Okay, welcome back to Random Walks. I have a little thought problem to propose to start out our discussion, but let me, while we're waiting for everyone to arrive, let me just say a few words about the central limit theorem. So the central limit theorem says that the probability that our standard random walk by its nth step has moved a distance greater than t times square root of n, square root of n being its expected distance from the origin, is almost equal to, it's asymptotic as n goes to infinity, to a normalizing factor, 1 over the square root of 2 pi, times the integral from t to infinity of e to the minus x squared over 2 dx. So this is the standard Gaussian. And we're out here at some point t, which is measured in units of square root of n, and it says this extremely rapidly vanishing tail of the Gaussian measures the probability that x of n is bigger than this. So, so last time we proved a very weak version of this, but one that's uniform in n, which was that the probability that, say, the absolute value of x of n is bigger than, say, 2k times the square root of n, that this is big O of 2 to the minus k. So the probability that your 2k standard deviations away from the origin is exponentially small in k. And one thing I want to remark about, I'm going to make a remark about our proof of this and how it comes very close to actually proving this. But one thing I want to point out about both of these is they easily imply what's sometimes called the strong law of large numbers, which is that S of n, which is that x of n over n tends to 0. And if you think of this in terms of coin flips, that at each step, the random walker flips a coin. If it comes up heads, they move 1 step plus, otherwise 1 step minus. Then this says that the average number of heads and tails after n steps converges to 50%. It's not that it's close to 50%. That follows easily from this, that at each step it's close to 50%. But you see, it could be close to 50% with high probability, and on certain rare occasions get far from 50%. That's why this is called the strong law of large numbers. It says that as you walk along an individual random walk, this ratio x of n over n tends to 0. And of course, it's not hard to believe because it's very unlikely that you're more than distance than k standard deviations away from the origin. And for x n over n to be large, you would have to be like square root of n standard deviations away from the origin. So, so let me just explain why this is true. It's implied even by this rather weak statement here, because you see the probability that the absolute value of x of n is bigger than, say, epsilon times n. For one particular n, let's call this Pn. What can we say about that probability? Well, epsilon we could rewrite as the square root of n. We could rewrite this as the square root of n times epsilon square root of n. And then epsilon square root of n would play the role of 2k. So k would be epsilon square root of n over 2. And so we would get that this probability is big O of 2 to the minus epsilon square root of n over 2. All you have to remember is it's big O of 2 to the minus some function delta times the square root of n. Now, it's true that 2 to the minus square root of n does not go to 0 exponentially fast, but it goes pretty fast anyway. It goes much faster than any power of n, for example. So this is big O of 1 over n to the p for any p, for example. You can say much more. It's not quite geometrically fast, but it's still very rapid. And in particular, that implies that the sum of Pn is finite. Okay, now what do I know about an event when I have, if I have a sequence of events and the sum of their probabilities are finite, what can I say about those events? What are the chances that infinitely many of them occur?
0.
0, that's right. That's the Borel-Cantelli lemma. So since this sum is finite, the Borel-Cantelli lemma says this occurs for only finitely many n. So that means that x of n divided by n is bigger than epsilon for only finitely many n. And since epsilon was arbitrary, that implies x to the n over n goes to 0. Okay, so that's the proof of the strong law of large numbers. The other thing I wanted to say was that we do have these exact formulas, the probability that say x2n is equal to 2i, taking into account the fact that that after an even number of steps, you have to land on an even point. This is equal to 2n, choose n plus I. You need n more positive steps than n more negative steps. So it's 2n factorial divided by n plus I factorial times n minus I factorial. Except everything has to be multiplied by 2 to the minus 2n. So let me call this probability a sub I. And what we see experimentally is that these a sub i's look rather like this Gaussian curve. Now, why is that the case? Well, one way to justify that is to observe this simple combinatorial fact that ai plus 1 over ai is what? You have to, well, first, what we notice is that this quantity is maximized when I is equal to 0. So A0 is the maximum. And now suppose that I is positive and you increase it by 1, this quantity actually goes down. Now, why does it go down? It goes down because you need to increase the factorial in the bottom. So you need to add an m plus I plus 1 in the bottom, and then you need to get rid of this n minus I on the bottom. So you multiply by n minus I on the top. So the ratio between successive terms is 1 minus I over n divided by 1 plus I plus 1 over n. So this proves rigorously that the probability goes down with I. But you see something even more striking, which is that this ratio is a decreasing function of I. Okay, now what happens if we were to look instead at the function log AI instead of the function AI? What we would find is that this function is maximized at 0. Here's a 0. And then it goes down. And so it goes down by some amount. And then this fact that this was decreasing says the amount it goes down by each step increases. So it looks like this. The descent accelerates. Of course, this is a log, so it's allowed to go negative. In other words, this statement that this decreases says that log AI is a concave function. Now, could we figure out what that concave function is? Well, we can certainly get a pretty good idea for small values of I, because look at this logarithm. We get that the log of AI plus 1 minus the log of AI is a good approximation to the log of 1 minus x is just x. So this is approximately minus I over n. And then the log of this is approximately minus I plus 1 over n. Oh, let's forget about the minus 1. So it's approximately minus 2I over n. Certainly the first few values of I don't matter very much. And after that, I and I plus 1 are nearly the same. And so what you get from this is that log a sub s, let's say, is approximately equal to the log of a0, which is some constant, minus the sum from I goes from 1 to s of minus 2I over n. And what does that look like? Well, this is approximately, we're just summing up the integers from 1 to s. So this is approximately minus 2s times s plus 1 over 2n. So it's approximately, let's just say, minus 2s squared. So our conclusion is, minus 2s squared over n. Our conclusion is that this graph here looks like a parabola. And the parabola it looks like is something like minus 2s over the square root of n squared. And so that means that AI itself should be something like e to the minus 2s squared, 2s squared over n. And this, of course, is a Gaussian distribution. So in other words, this simple difference formula here implies that a good approximation to the probability of reaching site I is given by something that looks like e to the minus a quadratic function. That kind of explains the origins of the central limit theorem. And what we did to get our crude version of the central limit theorem is we went up to a certain point here and we said, look, this function is decreasing, its slope here is some number. We then know it continues to decrease at least that fast. But of course, we could have waited until here and then said it continues to decrease at least that fast. And the actual theorem, that's why the actual theorem has an e to the minus x squared in it instead of an e to the minus ax. So I just want to point out that the easy version of CLT can be boosted to prove the following. The probability of x of n is greater than or equal to, say, k times the square root of n is less than or equal to big O of lambda to the minus n for any lambda greater than 1. So if you didn't like the 2 to the minus n, you'd rather have 10 to the minus n there. Well, you can get that at the cost of changing the constant that comes in front of it. And again, the benefit of this is true for all n, not just in the limit.
Oh, Kurt, there's a question in the chat about one of the formulas.
Yeah.
Did we get an extra 2 when we did minus 2s s plus 1 over 2n equals minus 2s squared over n? I think it.
Oh, say that again.
Or Richard, do you want to?
It's erased. It's erased and it doesn't change the result much.
Okay, so let me say that there is an extra 2 floating around, which is that the number of steps here is not n, it's 2n. And there's also an extra step floating around because the location you're landing at is not I, it's 2i. And these all appear in different places in the original formula. And the net effect is cancels out and everything works. I believe it's correct in the notes. And I was trying to give the feel for it here. Other questions? Okay, so all of these theorems are good for understanding the distribution of a random walk in space. And what we're doing is we're fixing a particular time, n, and then we're saying, where is our random walker in space? But we also might want to do something like fix a particular point in space and ask where our random walker is in time. So you see, a good way to think about this random walk is we have the I variable, which is time, and then we have the space variable, which is x, and at a particular point in time, we have I, x of I. And so our random walk can be thought of as some sort of graph that moves around the integer points in the plane like this. And it's random. So the central limit theorem is about the following. Somebody picks a value of n, you draw this line here, and you see one number, which is x of n. Of course, this number is random. So then we look at what's the distribution of this number in space, and we get our Gaussian or Gaussian-like distribution. But there's a different kind of problem you could consider. You could draw a horizontal line like this. And now that will hit our graph in many points. And there's some different questions we could ask about time. We might ask, what's the probability that our graph hits this line, say up to time n? Or where do we expect the first point for this graph to hit this given line now? And one thing we know by recurrence is that if we wait long enough, the graph will eventually hit any given line. So there is, in fact, a well-defined time, T of m, when the graph first hits this line. So I want to investigate some questions of that ilk. And to warm up, I'm going to give you a breakout room question to discuss. So let's return to Gambler's Room. So here's a very cautious gambler from the Midwest. They arrive in Las Vegas and they have $1. That's all they have. But they got a free hotel room. So they're allowed to stay as long as they want. And so they go to our roulette wheel. And let's say this is the imaginary world where Las Vegas is fair. So they go to the fair roulette wheel and they start at this point 1 and they bet everything on red. Now it's possible with 50% chance that they run out of money and then they're done, they go home. So they lasted 1 spin. But it's also possible that they doubled their stakes. And now there's a 25% possibility that they lose twice in a row on the next 2 spins. And then they're done, and they have to go home. But it's also possible that they might win on the next spin. And this particular gambler is pretty close to losing. They only have $1. But they have no goal in mind. They just want to keep playing. And so they don't care how much money they make. If they get up to $1,000, they just keep playing anyway. Okay, but of course it's extremely unlikely that they're going to get up to $1,000 before they run out of cash. So the question is, how many spins on average does our cautious roulette player get to play? So how many spins on average until all is lost? So you can see already that the probability that you lose after just one spin is 50%. So this is some concrete number, because it's kind of canonical. I mean, I just used the 0.1. I'm using fair random walk. And so I'm going to ask you to go to breakout rooms for 5 minutes and discuss this and try to come up with an answer and an explanation. Okay, so I'll remind you, when you do go to breakout rooms, make sure you introduce yourselves around, pick a reporter by any mechanism you wish, and then in 5 minutes, we'll come back and have a little discussion of the problem. Okay. Let me see here. Okay, I'm gonna just for fun, I'm gonna make the groups a little bit larger than usual this time. Okay. Okay, welcome back. So please raise your hand using the reactions if you are a reporter. I should see 3 hands coming up. 3 hands. So far I only see 2 reporters.
Oh, we forgot to choose a reporter.
Oh, who said that? Alec, I guess you're the reporter. Okay. So Alec, would you like to go first?
Okay, so I guess one idea that like Catherine suggested was using like Doobe's optional stopping theorem.
Okay.
But I don't personally, like I don't really know. It's, I guess
Okay.
the way I try to do it is like, well, let's calculate the probability that you hit 0 after 2n+1 steps.
That's a good point. It's going to have to be an odd number of steps.
Yeah, so the probability you hit 0 for the first time after 2n+1 steps, that's a, well, for the first 2n steps, you have to have at least as many right moves as left moves, because otherwise, like, you hit 0. And then, so the number of ways you can do that is the nth Catalan number, which is 2n choose n divided by n+1.
Wow. Okay.
And then you divide the whole thing by 2 to the 2n+1 because you have 2n+1 steps.
Okay, so the Catalan number was again, is Cn is, what is it again?
2n choose n
Divided by?
n+1.
Okay.
So that's the number of possible like moves you can take for the first 2n steps.
Okay.
And since the actual path has length 2n+1, you divide this by 2 to the 2n+1.
Okay.
And then you multiply by the length of the path, which is 2n+1.
Wow. Okay, and did you come to a conclusion from these calculations?
No, but like I don't know, it seems like like it at least like unless I screwed up, like the expected value is not finite, but
in which case we could say it's infinite.
yeah.
Okay, interesting. Somebody else want to weigh in? How about Benji?
Yeah, so that's not what we talked about, but so we tried to set this up as a recurrence like we did last time. So so if we're at, let's let f of n be the value that we're trying to find. So it's like the average of the 2 neighbors around it, but plus 1.
So so f of n is the expected time starting in position n?
Yeah.
Okay, so this is your lifetime starting at n.
Exactly.
And we're trying to compute f of 1.
Mm-hmm.
Okay.
And it's like almost the average of its neighbors, but you got to take 1 step to get to either side.
So fn is 1 plus 1/2, fn minus 1 plus fn plus 1. Okay.
So, and then we set it up like, that's basically the recurrence that we saw last time when we were looking at this game. And then we see that the expectation is like proportional to how far you are.
Okay.
So that gets that it should be infinite. Or the other thing that we looked at was just like the expectation.
Wait, say that again. So this is the lifetime you last, right?
Yeah.
This is how long you, so the value we're interested in is f of 1.
Yeah.
And then you say that this should be infinite because?
So we didn't complete the process there, but we also talked about like the expectation of the game itself, which is infinite.
Of the payoff or the length of the game, or?
Like the payoff of the game. Because if you go, the probability that you go like directly to n steps to the right is like 1/2 to the n, and your payoff at that point is 2 to the n. So it's like you kind of like expect to gain a
that's very interesting, right? Okay, continue.
So at every step, like because of that, when you're adding all these numbers up for all n, it's kind of like adding almost like proportional to some constant every time,
right?
Which means that the whole game you have infinite expectation, And if at every step you had a positive probability of going to 0 and zeroing out,
Yeah.
then that wouldn't be the case, which means you should.
Okay, that's very interesting. So we do know there is a number, tau, which is the least n such that x of n is equal to 0. And we also know that the function f of x equals x is harmonic. And last time we observed that we could figure out the probability of the various payoffs because of the fact that f of tau is a martingale. That is that the value, it's a fair game, so your expected earnings, even up to a given stopping time, should be finite. So there's something very strange because this number is finite almost surely because of recurrence. And yet we know exactly what the expected value of f of tau is because f of tau is 0. Tau occurs, f of x of tau. Tau is the moment you return to 0. So this is the f of 0, which is 0. So we started with $1, and yet when the game terminates, we have nothing. So something strange happened, contrary to the theory of martingales. How about Richard?
Yeah, our group also set up the recurrence, and I think our discussion follows mostly what Benji and Alec already covered. We also wrote some codes to try to see.
Wow, great. I could have given you 6 minutes.
It's like most of the time it's 1 or 3, but then occasionally we have like 5.3 million or some very big number, which is
totally interesting. Yeah, that's great. I'm really glad you did that. Okay, but what's your guess about the expected time to first hit 0?
I think with the discussion so far, this expected time is infinite. Like my guess, the proof would be like if it's not, then using this stopping theorem somehow we can argue that the expected payoff in the end is equal to the expected payoff at the start, but we know 1 and 0 are not equal to each other, which means contradiction.
Okay. Very good. So a lot of interesting things came up in the discussion, but we will prove this in just a moment. The expected value is actually equal to infinity. So if you go to Vegas with $1 and all you want to do is have fun, the expected length of your stay is longer than your life. That's if the game is fair. And so random walks are recurrent, but they're very slowly recurrent. You may have to wait a really long time for the random walk to complete. And it's very strange and unusual in life to encounter random variables with infinite expectations, even though they arise all the time. There's this kind of prejudice to believe that everything is like a Gaussian, and then suddenly one of these black swan events happens, and your random walk, instead of terminating in 3 steps, lasts 10,000 steps. And if you thought that that was an exponentially small event, you're really in trouble. The other thing I want to observe is that when it comes to solving this difference equation is like a second order differential equation. It's like saying what the Laplacian is of f. The Laplacian of f should be -1. So it needs 2 boundary conditions to have a well-defined solution. And that worked well when we had 2 points to stop. But with no point to stop, there is no unique solution to this equation. We haven't given enough information to determine the solution from its boundary conditions. Okay, so what we're going to do now is compute many examples of the theory of distribution in time. So one of the most, and I say, maybe I'll say and space. So one of the most important numbers that comes up over and over again is the probability that in exactly 2n steps, you return to the origin. So U2n is the probability x of 2n is equal to 0. And we know this exactly. It's 2 to the minus 2n times 2n choose n. And we proved when we studied recurrence that this is asymptotic to 1 over the square root of pi times n. So we have a very good understanding of the probability that a random walk returns to the origin after 2n steps. It's pretty small, but it's not that small. It goes down like 1 over the square root of n. But what's interesting is that many other similar probabilities can be expressed exactly in terms of U2n. And so a related probability is F2n, and this is the probability that the first return, 0, occurs at step x2n. So in other words, x2n is equal to 0, but xi is not equal to 0 for I equals 1, 2, up to 2n minus 1. Okay, so that's a path that has to be either always positive or always negative up to the moment when it finally returns to the origin. And what we're going to prove eventually is that F2n is equal on the nose to 1 over 2n minus 1 times U2n. So it's a small, it's a very simple expression in terms of U2n. And what you'll notice is that it's very similar to this Catalan number that, that Alec mentioned. And I suspect there's a neat way to make that connection more precise using one of the 10 different definitions of Catalan numbers. But we're going to study why the first return to the origin is so closely related to the probability of returning at all. Let me also remind you another reason this number is important is that when we look at this function AI I was just mentioning, the probability of returning to after 2n steps being at location I, U2n is this number A0 of n. It's the peak. It measures the size of the peak of the Gaussian-like distribution that we get. Okay, so let's notice that since this goes like square root of n, this guy goes like, let's say 1 over, this is like 2n. So it goes like 1 over 2 times the square root of pi, and then there's an additional value of n, and then this is times 1/2, so n to the 3/2. Okay, that's the probability that we first make it back to the origin at time 2n. And so as a corollary, indeed, the expected value of tau, which is the first return, 0, this is given exactly by the sum over the probability that we first return at time 2n times the number 2n. 2n F2n. The sum of these, we eventually return, by the way, that we eventually return, so the sum of the F2n's is equal to 1. And this just integrates the return time against that probability distribution. But this is like the sum of 1 over the square root of n, and that's infinite. In fact, it diverges rapidly. It's not even like the harmonic series. So yes, the time of the first return to the origin, the expected time of the first return to the origin is infinite. Now let's also make a back of the envelope calculation of the probability that when we take a random walk, that the first return to the origin occurs later than some fixed time capital N. So the probability that F2N is, say, greater than or equal to some integer capital N. So it takes quite a long time to come back. This is on the order of the sum of F2N over, sorry, what am I trying to say? The probability that tau, the time of first return, is greater than or equal to N is the sum of the probability of the first return being at time 2N, where 2N is greater than or equal to N. And this is like the sum of 1 over n to the 3 halves over n is greater than or equal to n, or n over 2. In any case, it's like integrating this function. So this is like 1 over the square root of n. So for example, the probability that the first return to the origin is greater than 10,000 is on the order of 1 over 100. So when you take a random walk, there is a 100% chance that you go on this wild adventure where it takes you 10,000 steps to get back to where you started. You get a little bit away from the origin and then you get totally lost, and it takes you a really long time to come back. And what that means is that if you simulate random walks on the computer and you do it, say, 10 times, or 100 times, you'll easily find a random walk that takes a tremendous amount of time to come back to the origin. And so this is in the notes and on the web page. Here is an example. I just quickly ran 100 random walks the other day. And this is a genuine random walk that takes over 6,000 steps to return to the origin. And this was out of 100 random walks. So it's really quite a remarkable phenomena, maybe a little bit unexpected, that random walks often spend a tremendous amount of time strictly in the positive regime or strictly in the negative regime. And in particular, if you take a random walk of length n, it is not true that when n is large, it's positive 50% of the time and negative 50% of the time. The distribution is of which side of the origin is on tends to be very skewed, and there's something called the arcsine law, which we won't make precise, that explains exactly how that happens. So this is not an uncommon event at all. You see this 1 in 100 times. The other thing I should say is that we will shortly be talking about Brownian motion, I hope. And this path is starting to look like a continuous path. And this is, in fact, a good approximation to Brownian motion on the real axis. And the main thing to notice about this path is that it has very sharp ups and downs. It goes up and down quite a bit, so it doesn't tend to get anywhere because it tends to keep retracing its steps, but it moves really fast. In fact, I mean, just here we've rescaled everything, but you can see it sort of, if we try to make the graph fit in a square, then it has really sharp ups and downs. And that's because we have to scale a lot more in the space direction than in the time direction to get this thing to fit in a nice graph. Okay, so we'll see that in more detail when we come to Brownian motion. Good, okay, so I want to now prove this theorem about the first return to 0. And it's an example, the proof will be an example of a general pattern that's used frequently in probability theory. It's called the reflection principle. So I'm gonna warm up by proving a related theorem. So we can also ask, ourselves, what is the probability that here my random walk wasn't allowed to touch 0. Suppose I allow a random walk to touch the origin, but not to become negative up to time n. Or up to time 2n, let's say. See, if it's, yeah, let's say up to time 2n. It might even be 0 at time n, 2n. So the theorem is the probability that x of I is greater than or equal to 0, for I is of course, it starts at 0. So 1, 2, 3, up to 2n is equal to u to n. In other words, it's equal to the probability that x of 2n is equal to 0. Okay, so there are many proofs of this theorem and of the allied theorems that we're going to discuss. And the proofs are of many different types. So one way you could try to prove this theorem would be to find a complicated expression for this probability. It would involve lots of binomial coefficients. And then you'd stare at that expression with your Putnam winning team mind, and you'd find all sorts of simplifications, and then it would finally turn out to be this. But there's a better way to try to prove this theorem. The better way is to try to prove that every path that does this can be canonically associated to a path that does this, and vice versa. So if there's only finitely many paths of length 2n, and they each have the same probability. So if you can match paths that are non-negative with paths that return to 0, then you have a conceptual proof that these two probabilities are the same, and you don't have to do anything with binomial coefficients. And it's the search for those conceptual proof that's facilitated by these reflection arguments. It's called the reflection principle, although I'm not quite sure how to say exactly what the principle is. Let's just see it in action. Okay, so let me say Z is the set of paths with x to n is equal to 0, and P is the set of paths with xi greater than or equal to 0. And I'm going to construct a mapping from Z to P, and this is going to be 1-to-1 and onto. And that'll suffice to prove the theorem. Okay, and now here's the construction, don't blink. So I think this theorem was known for a long time, and then one of my former colleagues at Princeton, Ed Nelson, gave this proof. So we have a path that returns to 0 at time 2n. Okay, so it starts at 0, goes up for a while, and then maybe it goes down for a while, and then goes up for a while, then maybe it goes down for a while, goes up for a while, and then finally it returns to 2n. Now this path has some minimum value. Let's call that minus m. So minus m is the minimum value of xi for 0 less than or equal to I less than or equal to 2n. It certainly is, m is certainly greater than or equal to 0 because we started at the origin. And now we're going to do something really clever, which is we're going to take this part of the path and we're going to reflect it through this line. And then we're going to translate after reflection so that this point here becomes this point here. Okay, so I take this path and then I draw its mirror image at the end of the path that I have already. So it now goes like this, and then it goes back down like this. Okay, now remember that this path went down to minus m, starting at 0. So this path starts at 0 and it goes up to m. So this height here is m. And this minimum first occurred at some moment k. So this new path goes out to time 2n plus k. Okay, and now, by the way, the path might assume its minimum more than once. But I have a canonical moment to look at, which is the moment when it first assumes its minimum. That's another characteristic feature of these arguments. And now we have a non-negative path, a path in P staring us in the face. Namely, we consider this path here, and we consider this to be the origin. So this path starts at time k and goes out to time 2n plus k. So it's a path of length k, and it stays above its minimum, of course. And so if we call this height now 0, it's a non-negative path. So we just make this the new origin for P. Okay, this was our path C, and we get a new path P. And that gives a map from Z to P. And now you might wonder, can we go backwards? Well, we can, because you see, suppose you were given this path here. What we want to know is, where is this piece that we added on? Let me put that in red, actually. Where is this piece that we tacked on? Well, notice that for the new path, this total height here is 2m. It's a path of length, it's a path of length 2n, so its height, no matter what it is, has to be an even number. It's 2h. And so what we do is we look at where we go down to 1/2 the total height, which is h, and we draw this horizontal line. And since the path started at 0, it has to cross the line at height h at some point. And in this picture, the last time it hits height h is at this moment here. And so then we take this guy, reflect it, put it back at the beginning, and we've got a path that begins and ends at 0. So this is in fact a bijection, and therefore the two probabilities are the same. Okay, so this is a beautiful and elegant example of the reflection argument. And one thing you see is this number U2n and its variance, they keep coming up over and over again. There's many ways to talk about this number U2n. Also, I would say that the probability that this random walk is always positive, we now know this is going like 1 over the square root of n. You might think that, maybe the probability that the random walk is always positive should be exponentially small in n. You have n chances for the random walk to go negative. But that's not true, because once the random walk starts to be positive, the fact that the remaining steps are positive, those are not independent events. They're dependent on how far you've drifted from the origin to start out with. So it's that correlation that allows this number to be so big rather than exponentially decaying in n. Okay. So that's our first reflection theorem. So now comes the famous Ballot Theorem, which we've all seen in practice lately. This is called the Ballot Theorem. It has a long history, which I won't attempt to recount. It's nicely discussed in Feller's book. So let's let P greater than Q be the number of votes cast for 2 candidates. The election is not a tie. The P candidate won. The probability that the winner leads at all times during the ballot count is P minus Q over P plus Q. Okay, so Biden is going to win, but he has this tiny edge. Now, what's the probability that, he has a 1% edge? What's the probability that as the votes are being counted, he's always ahead? Well, it's very small. He has this edge of 1,000 votes, and the total number of votes is 100,000. And so there's a 1% chance that he would stay in the lead at all times. And so it's very likely that the other candidate appears to be leading at some point in the evening, even though the final outcome it will be for the first candidate. So you have to have a really overwhelming lead to have this probability be anywhere close to a half, let alone 1. Okay, now what does this have to do with random walks? Well, it's very simple. This corresponds to a random walk of length n, which is P plus Q. And so P is the number of positive steps, and Q is the number of negative steps. And so the final outcome at time n is the difference, which is P minus Q. Okay, so again, we can think of the tallying of the votes as taking place in space and time simultaneously. So we look at this random walk starting at the origin, and the first vote gets counted, and then the second one, and maybe the count leads for all time. But it might not. It might be that at some point there's a tie in the counting. Trump and Biden are all tied up, even though at the end of the day, we have to end up here at P minus Q. Okay, so how to count these random walks? So what we are interested in are the random walks that never touch the x-axis. That is, that never hit the origin en route to P minus Q. Well, it turns out to be smarter to look at the random walks that do touch the real axis. So first, let's T be the total number of walks from 0 at time 0 to P minus Q at time n. So we know exactly what that's given by. So we have P plus Q steps to take, and then P of them have to be in the positive direction and Q have to be in the negative direction. And we can arrange those to occur at any of the 2n possible points in time. Okay, so now let's look at something slightly different. Suppose that the first step in the random walk goes to -1. So right from the beginning, the leader is not leading. It looks like Trump is ahead. So we could ask how many paths follow this itinerary. They first go to -1, and then they end up here. So it still ends up here. So let's B be the number of paths from -1 to our final point, and p minus q. Well, that's the same as the original paths, but now we have to go up one higher because we're starting with a deficit of 1. So we get let me just quickly refer to my notes to make sure I write this down right. Actually, let me call this n factorial. So we started here, so we have n minus 1 further steps to take, and now we have to move positively now we have to move positively p times and negatively, sorry, I think I have this wrong. I think I need to move positively p plus 1 times and negatively q times. Oh no, these are not adding up right. So I have to move positively, no, I have to move positively p times and negatively q minus 1 times to get up to this point here. Right, okay. Because p plus q minus 1 is n minus 1, and p minus q minus 1 is p minus q plus 1. Okay, so that's the number of paths that start here and make it up to the origin. And notice that these all cross the x-axis. Now, how many other paths are there that cross the x-axis? Well, the other thing that can happen is that you start at 1, and then you're working your way up to here, but now at some point you hit 0, as in this path. And so in addition to these paths, which cross the x-axis, there's the paths that first go through 1 and then hit the x-axis. I claim that the number of paths that go through 1 and hit the x-axis is the same as the number of the paths that go through minus 1 and hit the x-axis. Why? Because to every path that starts at 1 and hits the x-axis, I can associate one that starts at minus 1, this time by reflecting through the x-axis. So B is also equal to the number of paths from 1 that hit the x-axis. Terrific. Okay, so we're almost done. We just have to figure out what this probability is that we're trying to compute. So let me call this, probability capital P. So P is equal to the total number of paths minus the number that cross the x-axis, which are of 2 types, those passing through 1 and those passing through minus 1, but those 2 types have the same number of paths, and the second type is easy to count. So a t minus 2b divided by the total number of paths. So all we have to do now, this is 1 minus 2b over t. So all we have to do now is compute b over t. So here's some room. So b over t is what? So b has a n minus 1 factorial in it, and t has an n factorial in it. So I need an n on the bottom. And then they both have p factorials in them, and that cancels out. But then t has a q factorial on the bottom, and there's a q minus 1 factorial on the top. So b over t is q over n. So I get, and n is p plus q. So I get q over p plus q. And so this is p plus q over p plus q, accounting for the 1, minus 2q, which is p minus q over p plus q. Okay, so that's the proof of the Ballot Theorem. Great, so we're almost done. It should now be possible to calculate the probability that a first return to the origin occurs at epoch 2n. Okay, so let's keep the ballot theorem on the board, and then we'll see that this has something to do with that. So by the way, one thing I want to emphasize here is that this is a conditional probability. This is not telling us something about all random walks of length 2n. What we've done here is we fixed the endpoint. We've required that we know what x is. We know that xn is p plus q, and then the question is, what's the probability, given that we know where the endpoint is, that the random walk is positive for all time. So if the endpoint is positive for all time, if the endpoint is positive, the probability the walk is positive for all time is given by this ratio here. So it's a conditional probability. Okay, so similarly, F2n is the probability that xi is a positive, well, let's say there's, I guess I should say 1/2 F2n is the probability that xi is positive for all I equals 1, 2, up to 2n minus 1, and x of 2n is equal to 1. So we want to know among all the paths that start at 0 and end at 0 at time 2n, we want to know among all these paths, what proportion of them never touch the x-axis. So those paths are of two types. They're the ones that, that first pass through the point 1 at time 1 and remain positive thereafter. And they're the ones that pass through -1 at time 1 and then remain negative thereafter. But our real question is, what proportion of all paths that begin and end at 0 after time 2n, what proportion of those never touch the x-axis? And that's not hard to answer. You see, let's think of this. Let's suppose that you first go to this point 1. So let's run the random walk backwards. So we have a random walk now of length 2n minus 1. And it starts at the origin, and then it never crosses the real axis, and it ends here at the point 1. That's an example of a ballot theorem. This is a ballot count where p was equal to q plus 1. So where p plus q is equal to 2n minus 1, and p minus q is equal to 1. This is an election where the winner came out ahead by exactly 1 vote. And of course, an odd number of votes had to be cast. Okay, so we're interested in knowing among all paths that eventually get to 0 and pass through 1, what proportion of them never touch the x-axis. But that's exactly the proportion where the winner is always in the lead in the ballot count. So that's 1 over 2n minus 1, the length of this path, and the rise, which is p minus q, on the numerator, the length of the path in the denominator. So F2n is 1 over 2n times the probability that x2n is equal to 0 and x of 1 is 1. And now the same argument applies for the negative paths. So it's also plus 1 over 2n minus 1 times the probability that x2n is 0 and x of 1 is minus 1. And of course, these two things just add up to the probability that x2n is equal to 0. The factor in front of them is the same, and so we get u2n over 2n minus 1. Okay, so that's our second application of the reflection principle in a slightly different way, and it can be used to calculate the time of the first return to 0. Okay, So notice that this Ballot theorem is much more general than what we need for this. Here we only needed the case where the leader was ahead by 1 vote. And this is a very powerful result which comes up over and over again. And it's good to have in your probabilistic toolkit. Okay, so the last time issue I want to examine is the first passage time. And I should say that all of these discussions about the finer behavior of one-dimensional random walks are perhaps somewhat surprisingly going to be in service of proving the relationship between discrete harmonic functions and continuous ones. And so we'll have to somehow use these one-dimensional arguments in two-dimensional settings ultimately. Okay, so the final thing I want to talk about, which is extremely natural, is the issue of first passage. And I drew this at the very beginning of this class. So we pick a point M, and we start our random walk. And then there's a very natural random variable, which is the time, T of M, when the random walk first hits the line x is equal to m. So T of M is the least n such that x of n is equal to m. Now, this is a random variable. So the main thing that we'd like to know is how it's distributed. But before we discuss that, let me make some remarks. So you might say, well, T of M looks too hard. I'm going to study T of 1, which is the first time the random walk hits the point 1. Now notice how similar this is to the roulette game that we started at the beginning of class. We did a random walk. If we just change the normalization of the x-axis, we did a random walk starting at 1 and asked when's the first time it hit 0. This is just sort of the same problem turned upside down. We have a random walk starting at 0, and we want to know when's the first time it hits 1. So there's a quantity tau of 1 is of great importance. It's just the first time the random walk visits 1. First moment, x of n equals 1. And again, by recurrence, this is finite almost surely. Okay, now here's a beautiful fact. Suppose we take some copies of this random variable. I take m copies of T1. And what I mean is I take some independent random variables that have exactly the same distribution as T1. And then I want to know what is Tm's distribution. And I claim that Tm equals, in the sense that it has the same distribution, as the sum of Ti of 1. Well, I guess from 1 to n. So in other words, if we understand the random variable T1, then we'll pretty much understand the random variable Tm. It's just the sum of many independent copies of the same random variable. And we can apply the central limit theorem and stuff like that to try to analyze Tm. Okay, now why is this true? Why is there, sorry, this should have been a T of n, tau of n. Why is this true? It's very simple. Suppose you have a random walk and it's going to make it up to level m. So what it has to do is it has to first make it to level 1. So it makes it to level 1 at some time T1 of m. And now, T1 of 1, tau 1 of 1. And now once it's made it to 1, start over. Consider this a new random walk starting from scratch using the independence of past. And we have to wait for it to reach level 2, but it's starting at level 1. So the time at which it reaches level 2 is distributed the same way as the time it took for the first path to reach level 1. So this is T2 of 1. the difference between these two times, the amount of additional time we needed to wait, was T2 of 1. And now we start all over again, and we have to eventually reach level 3. That occurs after some additional time, T3 of 1, also distributed the same way. And then finally, we keep going until we reach level M. So understanding the time the random walk takes to return to the point 1 is really the heart of the matter. And I guess in view of time, that's what we'll analyze next time. And then we should have enough tools at hand to go on and study harmonic functions and their limits on the lattice and show that in the continuum limit, they converge to ordinary harmonic functions. Okay, so I'll stop there for now, and I'll remind you I have office hours tomorrow at 4, and please also feel free to hang out after I stop recording.